And hello, everyone. And today I'm going to introduce my study. The title is A Study of Applying Eco-Driving Speed Advisory on Transit Signal Priority. I'm a speaker, Wang Xuanzhi, and I'm from Cheung Kong University from Taiwan. And here's the outline. First, I will give a brief introduction and then introduce the methodologies and experiment design, and then the result analysis. And I will give conclusions and suggestions for future studies. Okay, here comes the introduction. And transit signal priority has long been seen as a cost-effective way to improve buses reliability. It aims to reduce buses delays at intersections through adjusting signal settings. And under connected vehicle technology, we have eco-driving speed advisory, and it aims to improve energy consumption through providing driving speed advisory. Usually they are developed based on spot information, that is signal phasing and timing information. And some studies has integrate both of them and call them cooperative traffic control. And we have reviewed some TSP, transit signal priority papers, and then eco-driving speed advisory. And we noticed that some papers have proposed cooperative traffic control, but most of them are developed based on the assumptions that the buses are operation on the exclusive lane. So the motivation is to implement cooperative control on electric buses under mixed traffic circumstances. Here comes the methodology. And we call the system we propose in the study is cooperative active transit signal priority. And in short is ATSP-C. And it can be separated into three components. The first component is a detection of bus. Once the system detects the bus, and the RSU and roadside unit will predict bus arrival time and calculate its passing probability. If the probability is less than a user-defined threshold, then it will calculate TSP strategies. And in component 3, the RSU will send signal timing information to OBU, the onboard unit. And the onboard unit is assumed to be installed on all electric buses. So OBU will get the signal timings information and calculate eco-driving speed. And okay, this is the structure of the system. The first one is the computation of intersection passing probability. And basically we assume that the arrival time of the buses at the intersection is a random variable that follows normal distribution. So with the signal timing information, we can get the passing probability by cumulative density function and by integrating the green durations. So we can get a passing probability. And the computation of TSP strategies, we separated into 4 cases. And case 1 and case 2 will adopt red truncation, and case 3, case 4 will adopt green extension and red truncation. Here's flows of how to compute the TSP strategies. And step 1 is to identify the case, and then we will initialize these 2 variables. This variable YIIJK stands for the amount of red truncation, and this is for the amount of green extension. We will initialize them as 0. And in case 1 and case 2, we will try to increment it. Case 3 or case 4, we will first test if the green extension value has reached maximum priority value. And if it's not, so we will try to increase green duration. And else we will set it as 0 and try to truncate red duration. In step 4, we will compute the passing probability accordingly. And in step 5, we just repeat step 3 to step 4 until one of the two conditions is fulfilled. The first is passing probability has been larger than the user-defined threshold, or the second one is one of the two variables has equals maximum priority value Y max. And if this condition is fulfilled, then we will use minimization red duration strategy. Okay, here comes the eco-driving speed advisory. Similar with the TSP strategy, the system will predict bus arrival time at the intersection and calculate the passing probability. If the probability is less than the threshold, then it will compute the speed advisory. The algorithm of computing a speed advisory, the objective is to find advisory speed that can maximize the passing probability. And it's an enumeration result, the enumeration method let's select from a range. The range is 0.7 multiplied speed limit of the road and 1.1 multiply the speed limit of the road. Okay, apparently it's possible that the method can find a speed V that fulfill our requirement, so the system will advise gradually slow down the speed. Okay, here's an experiment design. And a real intersection located in Tainan City, Taiwan, is adopted as a case study. And this is the layout of the intersection. And this is how I implemented in the SUMO simulation. And this is a traffic value we adopted. And we will adopt two types of traffic value. The one is VC 0.9, the one is VC 0.5. And the signal settings is listed in the tables. And there are 4 phases. And the signal setting has been optimized by Pacer-5. And this is the parameters of the electric bus. Bus route number is 70, and it is a real bus, just like in this photo. And we set the parameters in the list, just like listed in this table. Okay, we designed several performance measures. The part 1 is vehicle-related performance, and the part 2 is buses. We will compute the electric energy consumptions. And we designed 4 parts of scenario. And the background signal plan is served as a baseline. And the second one is disable TSP, only enable eco-driving speed. And the third one is enable TSP, but we do not use eco-driving speed. The fourth one is both enable TSP and enable OBU. And we design 2 types of TSP. The first one is strong TSP. The Y max is 20 seconds, and the second one is 10 seconds. Okay, here's the result. First, we can find that significant reduction in bus delays, but we can find there's something different in VC 0.9 case and VC 0.5 case. In this case, the variation is large, but in the lighter traffic volume case, the variation is quite small. And we also can find like an interesting result is if we only use equal driving speed, but without the transit signal priority control, and we can find that the result is worse than the baseline. Okay, we also can find that disturbance on site traffic is high in VC 0.9 case. And reduction in average electric energy consumption is about 1.5%.
I'm sorry, we have 5 minutes remaining.
Okay, thank you. Okay, and the result in a strong TSP case is similar. I will just skip then, and it's just like the result in experiment 1. And here I want to mention is reduction in bus delays of strong TSP can reach to about 33%. Okay, here comes the conclusion and the suggestion. And the study focused on exploring the potential benefit on integrating eco-driving speed advisory system and transit signal priority. And the results show that in 0.9 VC ratio case, we can reduce bus delays at most about 20% and energy consumption about 1%. And then in 0.5 case, at most can reduce about 33% and energy about 1.5%. Here are some suggestions. And the first one is we can find that the variations of the result is high in 0.9 VC ratio case. So the improvement in the model is required, I think. And in this study, we assume that drivers fully comply with speed advisory. So we should explore the different compliance rates in the future. And I've noticed that the SUMO, the latest version of SUMO has support GLOSAR system. So I would like to give a try to comparison with GLOSAR that's supported in the SUMO in a future experiment. So here's my presentation. Thanks for your attention.